Okay, video number 2 for related rates. Let's get right into it. The height of a cylinder with a fixed radius of 12 centimeters is increasing at the rate of 4 centimeters per minute. Find the rate of change of the volume of the cylinder when the height is 20 centimeters. Okay, we were given a lot of information here. We're given the rate at which the height is moving of the cylinder. They gave us 2 pieces of information in this first sentence. The height is increasing at a rate of 4 centimeters per minute. That's the derivative of the height with respect to time. So we know that it's getting bigger, so it's positive. They told us that the radius is 12. It's fixed radius, so it's not moving. So we know a little bit about its derivative. We also know that the height is 20. And the question is asking us to find the rate of change of the volume of the cylinder. So they're asking us for this. Okay, let's draw a picture. It's always nice to see a picture of what we're dealing with. So if we want to know the rate of change of the volume, that means we need a volume equation. So the volume equation, the volume of a cylinder is pi r squared times the height. It's the area of the base times the height. They gave us the height was 20. Told us that the height was increasing at a rate of 4 centimeters per minute. Gave us the rate. They gave us the radius. And they also gave us the rate at which the radius is changing indirectly. It's not changing, it's not moving, it's fixed. So you have to be careful. Sometimes things are not moving, and if that's the case, then the derivative would be 0. Because again, when we take this derivative, we have a product rule situation again. We have 2 variables. You're going to have to use the product rule. And every time you take the derivative of a variable, you got to make sure we're dealing with time here. It's the independent. So you have a dt situation. So product rule here. Again, we have 1 times v to the 0 power, derivative of v with respect to time. This is the first piece times the derivative of the second piece. H to the first power is the same thing, 1 times h to the 0 power. And then we just took the derivative of an h with respect to time. That's the first times the derivative of the second. Plus the second, which is the h, times the derivative of the first. So pi is a constant, it just kind of hangs out. Derivative of the r is 2r, and we took the derivative of r with respect to time. So that would be the second, that's the h, times the derivative of the first. Product rule. All right, and again, we have all of those pieces. They told us the radius, they told us the rate at which the height was increasing, told us the height, there's the radius again, and we had to make a conclusion about the rate at which the radius was increasing or decreasing in this case. It was fixed, so it's not moving, meaning its derivative, the rate at which it's changing, is 0. So if you simplify this, you end up with 576 pi. You can stick that in a calculator if you like, but you don't really have to. And because it's positive, the volume of the cylinder is increasing at that rate. Okay, let's do another one. A 10-foot ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of ½ foot per second, how fast is the top of the ladder sliding down the wall at the instant when the bottom of the ladder is 8 feet from the wall? Okay, here's a picture. So here's our ladder leaning against the wall. It's 10 feet. The bottom of the ladder is sliding away from the wall. So this piece right here is going this direction at a rate of 1/2 feet per second. And this is the x, so this would be dx dt. That's the rate at which this line right here is getting larger, because this spot right here is going this direction, meaning this space is getting bigger. So that rate is happening at 1/2 feet per second. The question is asking, how fast is the top of the ladder sliding down? Because if you think about it, this ladder is not moving, it's sliding. the ladder doesn't change size. We're not like shrinking it or making it bigger. It's literally falling. It's like this piece is going this way, which in turn will cause this to go down. So the question is asking this, dy dt equals what? How fast is the top of the ladder sliding down the wall? When the bottom of the ladder is 8 feet from the wall, so they actually gave us this too. All right, so let's put this in some kind of organization. We know the rate at which the bottom is moving is 1/2. We're asked to find the rate at which the top of the ladder is moving down. They told us that the bottom is 8. And because we know this is 8 and this is 10, we can figure out what y is by using the Pythagorean theorem. I call this L, I could have called it C, whatever. Pythagorean theorem, that's a common one though. That's a 6, 8, 10 triangle. So now we know y is 6. Okay, so our situation here, they didn't ask us for volume, so we're not like finding the derivative of a volume. And they're asking us for the rate at which this is changing. So we really just need an equation that has that variable in it so we can take the derivative and have that dy dt, like take the derivative of that y. So we have dy dt. And we have that right here with the Pythagorean theorem. So the situation here is a right triangle. Let's take the derivative of the Pythagorean theorem. We don't need to use the product rule here. It's just power rules for all of these. But remember, every time we take the derivative of a variable, we got to do it with respect to time again. So this will be 2x dx dt, 2y dy dt, 2l dl dt. And we were given x, we were given dx dt, we figured out y. We're asked to find this. This is the variable that we're not going to know. They gave us L. We didn't talk about this yet. Kind of. I mentioned it. I mentioned that this ladder is not moving. It's sliding, but the actual size is not changing. So it's not getting bigger. It's not getting smaller. It's just a movement. And it's the bottom is moving, the top is moving, but the actual ladder is not changing. So that derivative is going to be 0. So they gave us all these pieces, you plug them in. Note that the ladder is not changing in size, so its derivative is 0. Simplify here a little bit. This is gone because it equals 0 on the right. This is 16 times 1/2. So that's where the 8 comes from. And then we have this piece, which is 12 times dy dt. So now this is just a regular algebraic equation. Like this is an algebra 1 problem really. 8 plus 12 something equals 0. This could be any variable you want it to be for a minute just because we have to solve for that. So subtract the 8, divide by 10. I'm sorry, divide by 12. So it's negative 2/3. And remember, final answer should be in units. Top of the ladder is sliding down the wall at a rate of 2/3 feet per second.